During this film, you will be required to take down readings from the screen. This frog is taking in water through its skin by osmosis. To prevent dilution of its body fluids, it also takes in salts by a process called active transport. We're going to investigate this process, paying particular attention to the intake of sodium ions. We shall carry out experiments on sacs of fresh skin taken from the frog's hind legs. We take a freshly killed frog and remove the back legs. Then we strip off the skin like this. We've now got a tube of skin inside out. It's wetted in a dish of Ringus solution. After it's been tied at one end, on the right there, so that we now have a sack of skin, still inside out, remember, a thin plastic tube's inserted through the open end and tied in position. Now the sack's filled with Ringus solution. It's tied off and put back in the dish of Ringus. This is the other leg. The skin's removed again, turning it inside out as before in the process. It's tied at one end, then it's turned outside out like this. Now this sack is filled with Ringus solution. We now have two sacks, one inside out and the other outside out. In our first experiment, we're going to use a radioactive isotope of sodium, sodium-24, which gives off gamma radiation. It's kept in a lead-shielded container. A Geiger-Müller counter registers its radioactivity as we take it out. It's sodium-24 chloride, radioactively labelled common salt solution. A measured volume of the solution is put into a known volume of Ringus solution in this glass vial, and an equal volume into a second vial of Ringus. The two vials are clamped in position here, where they can be stirred using a magnetic stirrer unit. The sack with the skin inside out is suspended in one vial, which contains radioactive sodium ions, remember, and the outside-out sacs hung in the right-hand vial, which also contains radiosodium. If sodium ions pass through the frog's skin, the liquid inside the sacs will become radioactive. After 1 hour, the sacs are removed and rinsed and placed in clean containers. At the same time, some of the surrounding Ringus solution from each vial is put in two other separate containers. And there's a fifth tube there as a control to check on normal background radiation. You must now get ready to take down readings from a scintillation counter. Each tube in turn will have its radioactivity measured for a period of 10 seconds. First, the tube with the inside-out sack of frog skin. Let's see how much radioactivity has passed through the skin to the inside of the sack. Write down this number of counts. Next, the sack of frog skin, which was the right way out, outside out. take down the reading. Now for the sample of Ringer's solution in which the inside-out sac was immersed. And the Ringer's solution in which the outside-out sac was suspended. Finally, the background count. You can see that it's very low. In fact, we can ignore it. Afterwards, use the notes in the experiment booklet to calculate the flow of sodium ions into the two sacs, using the readings you've just taken. Now for another experiment. This time we shall measure the electrical potential difference between the outside and the inside of a sac of skin taken from another frog's hind leg. Dipping into the Ringer's solution surrounding the sac, there's a thin plastic tube containing saturated potassium chloride solution in an agar gel. This connects the solution outside the frog skin to a calomel half cell. A similar tube containing potassium chloride gel connects the solution inside the frog skin to a second calomel half cell. Using this setup, the potential across the skin, the transepithelial potential, can be measured on this voltmeter. Here it is in millivolts, around 20 millivolts. It fluctuates slightly under the conditions of the experiment. We're now going to add the drug warbane to the outside of the sac of frog skin. In it goes. There's no immediate change in the transepithelial potential. We let the experiment run for 1 hour, and there's still no change. It's still about 20 millivolts. Note that. No change if warbane's applied to the outside of the frog's skin. But we now add the same amount of warbane to the inside of the sac, so that it's in contact with the inside of the frog's skin. Get ready to write down what happens to the transepithelial potential as time passes. We start the clock. 0 time. Potential still around 20 millivolts. Write it down. Now, after 45 seconds, somewhere around 17.2 or 3 millivolts, estimate it, write it down. One and a half minutes. Two and a half minutes. Five minutes. 7.5 minutes. The potential continues to fall. Ten minutes. Fifteen minutes. Twenty minutes. We continue for 1 hour, and by then the potential has fallen to nearly zero. Now the frog produces a hormone called arginine vasotocin to control its sodium ion uptake. We're going to use this hormone for another experiment. We add it to the inside of the sac. Once again, you must record how the transepithelial potential changes with time. It starts at 20 millivolts again. Now, after 5 minutes, little change. Ten minutes. It's increasing. "15 minutes. Still going up. "20 minutes. "25 minutes. And 30 minutes. Now use your readings and the notes in the experiment booklet to see what these experiments tell us about the active transport of sodium ions across the skin of a frog.